So let me start. Let me recall that we consider the following energy of knots of closed loops. EQ of gamma equal to double integral over gamma 1 over the tangent point radius at 2 points x and y raised to the power q integrated with respect to the arc length measure, and the formula for RTP is the following. You have 2 points on the curve, x equal to gamma of t. This is the direction of the tangent, so this is the line gamma of t plus the real line times gamma prime of t. And if you have some other point y here equal to gamma of s, then 1 over RTP of x and y is equal to twice the distance from gamma of s to gamma of t plus the real line times gamma prime of t over gamma s minus gamma t squared. That's what you integrate. And we finished with the following picture. We finished with the diamond property, something that I call the diamond property. And this is the following thing that I want to take as my starting point, and I will use it a few times. So if you take your exponent bigger than 2, then you will find constants, let me call them delta of q and c of q, and they have the following property. If you take the distance of 2 points on your curve smaller than or equal to this delta of q times the energy of gamma to some negative power, which was 1 minus 1 over q minus 2, then I will make a picture in a second. Gamma intersected with the ball center x radius 2d and intersected with the second ball center y radius 2d is contained in the intersection of two cones. Say cone vertex x, axis given by y, and the angle phi intersected with the second cone with those 2 points reversed, and you can take here phi equal to this second constant c of q times the energy of gamma 1 over q plus 4 d to some positive power, which was given by q minus 2 over q plus 4. But maybe the formulas are not as important as the picture. So this is x, this is y. These are the two balls, and if you look for gamma in the intersection of the two balls, it has to be located in the intersection of the two double cones. Oh, so this is one cone, this is the second cone, should be parallel. So gamma has to be has to be here and nowhere else. And I also told you and tried to explain that this implies that the arc length parametrization is everywhere differentiable with the derivative of class C0 kappa and uniform norm bounds if energy bounded. So actually, let me make two remarks. Remark one, the proof that I showed used really Q strictly greater than 2 because we were summing a geometric series. And we were relying on the fact that this exponent kappa is positive, so it breaks down for Q equal to 2, the proof. But not just the proof, the result breaks down. For Q equal to 2, you can have curves of finite energy for which the derivative is not defined everywhere, and this is due to a subtle analytic fact that that Sobolev spaces in the critical case are usually not embedded in L infinity, but I'm not going to go deeper there. Another remark is that I also told you that you can. Another remark was that you can prove that gamma prime is Helder continuous with a better exponent, lambda equal 1 minus 2 over Q. And I also don't want to explain it because this would eat up too much of my time. Basically, the idea is that in order to get to this picture, if you remember correctly, we were using the basically the influence on the energy of little portions of curve located just here, close to points X and Y. Not everywhere, definitely not everywhere. And in order to get from here to here, you need to use more. And basically the idea is to use a technique from the calculus of variations or geometric measure theory called slicing. And it tells you that if an integral is bounded, then the integrand has to be bounded on sets of large measure, because otherwise you would violate the energy bounds. And so if you go from here to here, then you have everywhere this regularity of gamma prime, but also on a very large set, 1 over RTP to the power Q is very close or not very different from the value of the energy. And you use those both observations and you combine them, and you have to compute for half an hour or 40 minutes, and then you are done. But I want to state and discuss a second theorem, namely, suppose that you have gamma j simple loops, no self-intersections, energy of gamma j is smaller than some or equal some constant m for all j. And I want to state the following variant. Suppose that they converge uniformly to a limiting curve on a given interval 0L values in R3. Then, first of all, gamma is C1, and gamma j prime converge uniformly to gamma as j goes to infinity. So if you have energy bounds, you can improve uniform convergence to C1 convergence. Second, gamma is simple. So no double points, no self-intersections can occur in the limit. And the last condition says that the energy of this limiting loop gamma is less or equal than the limmas inferior of the energies along the sequence. So your energy is lower semi-continuous. So maybe I try proof of that. You mean here? Thanks. Sure. So the proof is as follows. So first of all, you have this inequality, gamma j prime of t minus gamma j prime of s smaller than some constant depending possibly on q and on the energy bound, but if q is fixed bigger than 2, t minus s to some positive power. So this gives you equicontinuity. So you can think of the classic Arcela-Ascoli compactness, and then you know that each subsequence of gamma j prime has a subsequence gamma j prime, I don't know, let me add another index for a second, converging uniformly to some function f. But since you know that the functions themselves converge too, you know that the functions converge to something that has a derivative, and this derivative has to be equal to f. So, because this happens for each subsequence, you can start with the initial gamma j prime, take any subsequence that you like, apply Arcela-Ascoli, select a convergent subsequence. It converges to something, but you know that the gamma j converge themselves, so this f has to be the derivative of the limit. And since this applies to each subsequence of gamma j prime, then you know that the whole sequence gamma j prime converges uniformly to gamma. Cannot converge gamma prime. It cannot converge to anything else. Let us now see that Heiko will need it also, I think. Let us now see that the limit curve is simple, and in order to do this, we will use the picture above. So I want to show that there is a number, maybe say epsilon 0, depending on my exponent q and my energy bound m positive, such that for each j, 1, 2, and so on, and for each st in my parameter domain, gamma j of s minus gamma j of t is uniformly bounded below by the smaller of two numbers, epsilon 0, and say maybe s minus t over 2. And once I have it, I can of course say that if I prove this, then I will let j go to infinity, and I will have the same thing for gamma by passing to the limit, and this implies that gamma is simple. So how do I go about it? So first of all, please recall that I'm dealing with the arc length parametrization, and so the first observation would be that C0 kappa bounds for gamma prime imply by Lipschitz bounds for gamma locally, and by this I mean the following. So obviously you have t minus s at least gamma of t minus gamma of s, because this is the arc length parametrization. This is of course equal to integral from s to t of gamma prime. And by the triangle inequality, this is bigger or equal to the integral of gamma prime, but at some fixed point, say s for example, minus the integral from s to t of gamma prime minus gamma prime of s. So this of course gives you t minus s here. And this, because the difference here is very small, this is like a positive power of the difference between the parameters. So it is estimated from above by something like that. And it gets multiplied by the length of the interval. So it's, for short intervals, it is much smaller than t minus s. There is a big constant, but if you have energy bounds, this constant is a constant. And it tells you what scale you have to use in order to have this second thing, say, at most 1/2 of t minus s. So this is 1/2 of t minus s. So if I have Helder bounds for gamma prime, then I have locally by Lipschitz bounds for gamma. So my only concern is that, well, if this is short, then obviously I have this bigger than this, and I'm happy. I have to see what happens where possibly locally, I mean for t minus s smaller than some epsilon 1, depending on q and m. I have to see what would happen when the difference of parameters is large. And to this end, I consider a function of two variables, gj of s and t, equal for convenience to the square of the difference between gamma j and gamma t. I take here s and t belonging to the set sigma of all couples in the square 0L, such that s minus t is at least epsilon 1, which is a compact set in a plane, and this is a continuous function. So I can select for each j a couple of points, sj and tj, such that this is the lower bound of gj on sigma. How are these points located? Well, the first possible case is that the points are such that they are at the boundary of sigma, so that the difference is precisely epsilon 1. But if the difference is epsilon 1, I'm back to square 1, and I know that C0 kappa bounds for gamma prime imply an inequality of this kind, so again I'm back to this bound here. So everything is okay. The second case is where this difference might be bigger than epsilon 1. If it is bigger than epsilon 1, then I'm in the interior of this set, and I'm allowed to say the following. This is a function of two variables. It has a minimum somewhere. I can compute the partial derivatives, and they should be 0. So I differentiate this. When I differentiate this, with respect to s, I obtain gamma j prime at s perpendicular to gamma j s minus gamma j at t, and the same condition for t. And now let me go back to the picture. Oh, sorry. Okay. So basically two things may happen in this case. Maybe a little bit higher. A little bit higher. So there are two options. Option one is still visible here. Option 1 is the following. Either the distance d equal to gamma j of s minus gamma j of t is smaller than delta of q times the energy of gamma. Then the scale is sufficiently small so that This is gamma j of S now. This is gamma j of t. So the scale is sufficiently small that we see a picture like that. But look what we have here. We have gamma j prime, which is a unit vector showing like that. And gamma j prime of t also showing like that. So this is impossible because the tangent vector has to sit in those cones if the curve is contained in the cones. And it is the contradiction with the diamond property. So this leaves me with gamma j of S minus gamma j of t equal to the square root of gj of st bigger than this delta of q. This was a negative power. Sorry for that. Energy of q. And this is the desired lower bound because all the energies are bounded. So we have uniform lower bounds of that kind. Somehow, maybe if you don't want to think about all those computations, a very simple thing that I could say for those of you who don't like computations is the following intuition, that in some cases where the parameters are close, my integrand for a smooth curve is close to curvature, but it also penalizes, for example, the following behavior. If I have a closed loop like that, then here I have the classic curvature close to 0, but 1 over RTP, nevertheless very large, because my integrand understands that there is another strand of the curve nearby. Yeah, I draw a circle which is tangent here, and it touches many points here, and if those two strands are nearly parallel, then I get a huge contribution to my energy. Even if they look like that and they are too close, that's the contents of this message. Even if they are like that and they are too close, I get too large contribution to my energy. So the last part is to see that really the energy is lower semi-continuous. So maybe I try and erase that. And this is much simpler if you know that your curves converge in C1. And to do this, I just want to sketch it. So if, say, RTP, let me write that for the curve gamma j, at gamma j of t, gamma j of s is bigger than some positive delta. I keep it fixed for a while being, for infinitely many j, then of course the lim sup of RTP of gamma j at those points as j goes to infinity is also bigger than delta. But you know that the situation is as follows. You are dealing with simple curves, so maybe you have gamma of t here, gamma of s somewhere over there, and for large j, gamma j prime is very close to that point, and gamma j is very close to that point, and gamma j of s is very close to that point, because the parametrizations converge uniformly. And when you try to see where is the tangent line, say this is the direction of gamma prime of t and a fine tangent line to the limit curve at gamma of t, then because of the C1 convergence, this other tangent line is also very close. And now if you recall the formula for RTP, the fact that it is for those indices j which certify that the limit superior is big enough, for those indices j you really have gamma j of s at a certain distance from nothing degenerates. It's really like on my picture. Gamma j of s is far away from this affine line, and therefore it's elementary geometry, and I will not play with the constants, not try to make this very precise, but you can prove using geometry that the RTP of the limiting curve gamma at gamma of t and gamma of s is at least delta minus epsilon. And you can obtain this for any epsilon positive that you wish, because if you take a smaller epsilon, then maybe you just need to take this point closer here and this direction closer to that direction. So this implies the inequality between one thing and another. So this tells you that on the set where this guy is positive, like that, we have nothing degenerate, limit superior of RTP of gamma j at gamma j of t, gamma j of s, as j goes to infinity, is at least RTP of gamma of the limit curve at gamma t, gamma s on the set where RTP of the limit curve is positive, because then you can fix a delta, squeeze an epsilon smaller below, and then since this holds for an epsilon, then you are done. But of course, obviously on the set where this RTP of the limit curve is equal 0, the equality holds trivially. Yeah. So if you have this, then you say just apply phi2 apply Fatou's lemma. And since your integrand is the power of an inverse of this for the you will get the reverse inequality for the inverse, and you can apply the Fatou lemma and conclude. So, how about corollaries of that? I will maybe, this up, this down. Maybe before the corollaries, I will state one more remark, which is important here. And the remark would be, because of the C1 convergence, gamma, little gamma is isotopic to all gamma j for j sufficiently large. So the knot class is also preserved in the limit. And the first corollary is that EQ for Q bigger than 2 achieves its minimum in each knot class. And the proof is, of course, just a standard direct method. Of the calculus of variations. Take a minimizing sequence. You would now tell me that, well, taking a minimizing sequence is not enough. Is not enough to apply the theorem, and I would just say pass to the limit. Pass to the limit. And nevertheless try to apply this theorem, and when I take a minimizing sequence, I can always do one thing. I can fix one point. I can translate those curves so that they have, say, they all pass through the origin. And this is enough, in fact. Maybe I would add this here. Remark, it would be enough to assume that all gamma j have one common point. Because this is enough to conclude that
This is enough to conclude that the limit of any subsequence of gamma j primes is equal to gamma prime. You don't need the convergence of the whole sequence. You just need the convergence of the functions at one point. So if they have a common point, this is enough. Second corollary, it tells you that there are only finitely many knot classes under each energy level. Yeah. Yeah. I still work with, of course, the length is fixed. All curves have the same length equal to L. All the arc length parametrizations are defined on the same interval. So things don't, you know, straighten up, escape to... This is not the scale invariant case, so you have to fix the length. Yeah. So these are the two corollaries. But now, since Heiko will be talking about, he will finish probably by telling you that the energy landscape is, we don't know how complicated it is. So if you go back to the little movie that I showed you tomorrow, and you think that you would like to see the gradient flow of the energy, and you would hope that, well, it takes an unknot and it flows it smoothly, maybe to the round circle. Then you would need to know something about the energy landscape, and you would need to know that maybe that your gradient flow doesn't get stuck at some local minimum, or maybe at a saddle point. And it turns out that this energy has not only minima in each knot class, but in many knot classes it has other critical points. But nevertheless, it is possible to show that when you look at the energy minima on different knot classes, then this energy can distinguish the trefoil in any configuration from a round circle, from an unknot, just because the energy level is different. And in order to explain this, I need one more definition. E2 symmetric version of gamma will be equal to the double integral over gamma 1 over RTP xy RTP yx. This RTP is not symmetric. You take the derivative at the differential at one point, and you take the tangent at one point, and you fit the circle tangent at one point, the first point, and passing through the second point. And now I make the integrand symmetric. So this is the definition of yet another energy. What is the relation between this one and E2? Well, it is easy to see. You have the familiar inequality 1 over AB less than 1/2 of 1 over A square plus 1/2 1 over B square, like that. So using this inequality for the integrand and the Fubini theorem, you prove that the symmetric version of E2 is below the non-symmetric version of E2. And now let me also fix the length to be equal to 1, and I just then need to apply Hölder inequality to see that this is below EQ of gamma to the power 2 over Q. So this is how these different energies are related, and I'm going to show what is the inequality between the symmetric version of E2 and the average crossing number. Okay, so maybe I take this. So the average crossing number of gamma, of a closed loop gamma, is by definition equal to 1 over 4 pi integral over 0, 1 square, the absolute value of the determinant gamma prime of t, gamma prime of s, gamma of t minus gamma of s, over gamma t minus gamma s squared dt ds. And well, it turns out that there is a theorem due to Buck and Simon that E2, the symmetric version of gamma, is at least 16 pi times the average crossing number of gamma. Maybe I will put this up and this down. For those of you who have not seen the formula for the average crossing number, maybe the appropriate thing to say is that the geometric meaning of that is that you take your curve, project it on a plane, count the crossings in the projection that you obtained, and average this over all possible directions of the projection. So this is the average number of crossings that you see on a randomly selected projection of your curve, and you select different projections with the uniform probability distribution. And I would like to explain that because this takes us back to the definition of the symmetric energy and RTP. And so RST will be the unit second gamma of t minus gamma of s over gamma of t minus gamma of s. And I want to look at the plane spanned. So this is maybe gamma prime of t outside of this plane, and this is the plane spanned by r of s and t and gamma prime of s. And this is maybe the orthogonal projection of orthogonal projection of gamma prime onto this plane. This angle is called phi on my picture. This angle at the base is called alpha between gamma prime and gamma prime at S and RST, and there is one more angle here and it is called beta. So this determinant of gamma prime of T, gamma prime of S and RST, geometrically this is the volume of the parallelepiped spanned by the three vectors. So this is just the area of the base, which is RST, vector product gamma prime of S, times the distance from gamma prime of T to the plane P. And since I deal with unit vectors, this first area of the parallelogram is just sine of alpha, and the second guy here is sine of the angle phi. Now, since this is the orthogonal projection, since this is the orthogonality of the projection implies that sine of phi, which is this distance, is smaller than this distance, which is the sine of beta. So if I know this, then I know that if I replace here sine of phi by sine beta, I get something larger. So if I take sine alpha times sine beta and define it by gamma t minus gamma s squared, then I obtain something which is at least my integrand. Yeah, because one division by gamma should be cube, sorry. I somehow noticed things too late. To make it scale. So one division is already here, two more divisions are there, but now think about the formula for RTP. What was the formula for RTP? I still have a few minutes. The formula for RTP was the following. You 1 over 2 RTP was the distance from Y to L over x minus 1 squared. Yeah, that was the formula. So the two, this is like the sine of an angle divided, if this angle is alpha, this is sine of alpha divided by x minus 1. So the first sine with one distance gives you 1 over 2 RTP, and the second sine with another distance gives you the second RTP, and this simply means that 1 over RTP gamma t minus gamma s, RTP gamma t gamma s, sorry, times the second radius with the 2 points exchanged is bigger than 4 times the integrand. And now you integrate, and this 4 times the 4 pi gives you the 16 pi from the theorem. So this energy, as people say, can detect the unknot. If you have something really knotted, then no matter how you project, you obtain intersections, and for the unknot you don't obtain them. And this is more than enough to see that for the unknot the energy is smaller. So you could essentially you could hope that the flow will take you for an unknotted curve to the absolute minimum. But of course this is sort of a dream. We don't know it to be true. So maybe let me use the last few minutes to draw a few more pictures. I started by recalling the diamond property, and maybe I would like to finish with it. And to say the following. So you have your curve, and if you choose 2 points sufficiently close, you have such double cones here, and of course you can draw many of such double cones along your curve. You know, like that. So this picture continues like that, and of course if this length was d, then I told you that I can have this angle here, phi, which is smaller than some constant depending on q and energy, times a positive power of d, and in small scales for small d, depending on some delta 1 on q and energy, this is definitely smaller than, say, 1/4, and the curve is confined to sit in such a cone. So you have whole, we started calling it at a certain moment, necklaces of double cones. And these necklaces are not perfectly elastic. They have a certain stiffness, because you have a tangent vector here, you have a differentiable curve, and so this next cone can bend a little, but the tangent vector here tells you how much it can bend, not too much. So it's really like a physical necklace with a certain stiffness. And you can use this to obtain crude stick number bounds. because you can construct stick model. If it is a knotted curve, you can construct stick model using sticks of that length, many of them. It's of course a very crude bound, but nevertheless it is a stick bound depending only on the energy, and you can use it to obtain isotopy of C0 closed curves under energy bounds. Because one more thing that I would like to say before stopping is that if you observe your curve inside such a cone, it cannot do no matter what inside. If you slice that cone, like you slice a salami into round circles, it can intersect each salami slice only once, because otherwise you would be able to draw smaller cones inside and the curve would sit in one of them and not in the other one. So that's the geometry which sits behind lots of the analysis that we are doing for this energy, and I think that the next time Heiko is probably going to start to explain to you what are the energy spaces for that energy. So what are the functional spaces such that being of finite energy and sitting in this function space are two equivalent things. And this will take us to other critical points, not necessarily to minima. Thank you.